Hey folks, we are doing another worked example problem. This one is number 30 from chapter 12. It reads, the object shown is in equilibrium, and it really should say static equilibrium. What are the magnitudes of F1 and F2? I have a little addendum problem, a little bonus problem. What if the rod actually had mass? Notice that we didn't say in the original problem the rod had any mass. So what if the rod had a mass of 2 kilograms? How does that change F1 and F2? Let's focus on this first part and let's zoom in just a little bit on this figure. This is a recreation of the figure given in the textbook, obviously. We're given a force all the way over to the left tip here of this object, 40 newtons, and then I have F1 applied 2 meters from that leftmost side. Then 1 meter beyond that, at the rightmost side, I have F2 being applied up. So since this is an equilibrium problem, I have two conditions I need to satisfy. I need to satisfy that the sum of my forces equals 0. So put a little vector hat on there. And I need to satisfy that the sum of my torques are equal to 0, right? So maybe let's look at the forces here first. Right, let's look at the forces here first. I have two forces going up, one force going down. So if I think about the sum of my forces, right, I'm going to have the 40 newtons going up plus my F2 minus my F1, since it's pointing down, equals 0. Right, the sum of all three of these need to equal 0. So I need to solve for one in terms of the other. I'm going to just throw F1 on the other side. 40 newtons plus F2 equals our F1. That's as far as I can go. Right? That's as far as I can go in the force side of this problem, but I still have this torque side. Now, I need to place a pivot point. I need to place a point of rotation, and any point is as valid as another, right? I could place the pivot point here, right? I could also place the pivot point here, and finally I could place the pivot point here. I think those make the most sense. Of course, I could place the pivot point here, but that's not saving me any work, so why would I do it? Right? It's not laziness, it's efficiency, right? We're trying to be efficient here. So I'm going to place it right here. I'm going to get rid of any sort of torque that the 40 Newton force applies by setting that R equal to 0. Remember that torque is equal to R cross F in this case, right? And so if I'm just looking at the magnitude of these torques, by the by, right, we always can look at the magnitude of R times the magnitude of F times sine of the angle between those two. And if I think about putting my my point of rotation anywhere on this rod, this stick, whatever, I'm going to see that any force that I look at here is going to be perpendicular to the rod. And so sine of 90 will always be true here. So I'm just actually going to leave the sine out from here on out. Alright, let's keep going. So I have two torques, right? I have a torque from F1 that would want to make this thing rotate clockwise. And the torque from F2 is going to make this thing try and move counterclockwise if we're pivoting around here. So if I start to sum up my torques, right, I'm actually going to think about torque 2 minus torque 1 equals 0. That's how I'm going to set this up. So now I can just say R2 F2 minus R1 F1 equals 0. And now probably best if I substitute in. So let's throw this on the other side. Let's I guess let's trying to think a couple steps ahead here. Maybe R2 over R1, F2 equals F1. I think that probably makes a lot of sense to do. And now what I can say is let's substitute F1 from our force side of this problem in right here. Right, so I'm going to have R2 over R1 times F2 equal to 40 newtons plus F2. Alright, so F2, let's throw F2 on the other side. And maybe let's plug in some numbers here. Right, I'm going to say that from my pivot point, right, that's my R here, from the pivot point, I have F2 that is 3 meters away. F1 is 2 meters away, so I'm going to get a 3 meters over 2 meters times F2, but let's hold off for a second because I'm going to subtract this F2 from both sides. So I'm really going to pull an F2 out of this and say that's equal to 40 newtons. I like that. I like it. Cool, 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 cool. 3 over 2 is 1/2 minus 1, so I'm going to get 1/2. Right? I'm going to get 1/2 in these parentheses here. So what I'm going to do is say F2 is 40 newtons divided by 1/2. Right? 1/2. That's what we said this stuff was. If I'm dividing by 1/2, dividing by 0.5, I'm going to get twice as much. I'm multiplying by 2. Essentially, I get 80 newtons. Force 2 has to be 80 newtons. If force 2 has to be 80 newtons, then I need to add 40 newtons to get F1. F1, if F2 is 80 newtons, F1 has to be 120 newtons. So that is our first problem here. That is number 30 just by itself. 80 newtons, 120 newtons. So now let's move on to the bonus problem. What if the rod had mass? What if the rod had the mass of 2 kilograms? How does that change F1 and F2? Well, it changes because now I need to place one more force on this picture, right? Right at the center of its mass. Maybe let's do a die here or something. Center of mass, I need to place its weight, right? I need to place 2 times 9.8, so 19.6 newtons right at the center of mass. So now I have a total of 4 forces. I have a total of 4 forces, and so that just complicates the matter a little bit. All right, if I think about the sum of my forces now equal to 0, I'm saying that I have 40 newtons plus F2 minus 19.6 newtons minus F1 equals 0. Right? So that changes things a little bit there, right? That changes things a little bit. And if I think about my torque equation, right, and essentially this sets up the same thing. F1 is equal to something plus F2. That something is just a little bit less now. So if I think about my torques equal to 0, now I need a new pivot point. I could still use the 40 Newton force, the left tip of this whole thing, as the pivot point. Maybe that makes sense, right? In which case, now I have 3 torques. I have the counterclockwise torque from F2. I have the clockwise torque from F1. And then I have another clockwise torque from the weight, right, at the center of mass. And so if I'm thinking about this, if I'm thinking about this correctly, I'm going to throw both of those on the other side. I'm just going to say 3 meters times F2 equals 2 meters times F1 plus 1.5 meters. That's halfway through this rod. The center of mass of this rod would be halfway because we're assuming that we have a uniform mass distribution unless otherwise stated. So I'm going to say 1.5 meters times this force of 19.6 newtons. And so now I got to figure out, okay, what is this this new thing here? Well, I could say that F1 is equal to, if I do a little bit of rearranging, I get this 1.5 times F2 business, like we had last time, minus 14.7 Newton meters. I guess it would just be newtons, right? Because I'm dividing over the 3 on both sides here. No, sorry, dividing over the 2 on both sides. I threw that over. And then at this point, I can plug back into, this equation to solve for F1 or F2 here. Right? If I solve for F2, I end up getting F2 equal to 70.2 newtons. F1 then has to be 90.6 newtons. So it's a little bit different, right? A little bit different of our values here, right? F1 definitely is a lot lower. F2 is a lot higher, though. So they've kind of balanced out a little bit more, which is kind of interesting. So it's just the difference of adding in another force does make this a little bit more complicated. It gives us another torque, another force to deal with. Yeah, so that is number 30 and my little bonus problem to that. If you have any questions, feel free to reach out via email or swing into an office hour. Have a good one.